of it. But last time what we talked about was how do you, sorry, I'm not saying this correctly. What concurrency primitives are available for protecting shared state and governing access to shared state? And so we talked about a lot of those kinds of details, and especially how these affect interrupt context. How do you guard shared state when it's accessed from interrupt context versus process context and so forth? So it's a little bit challenging. And there's a lot of good examples. It's just like kernels are full of it. Basically, shared state that has to be accessed from different contexts concurrently, and particularly in multi-core systems, then it gets even more complex. So a lot of times it's linked list. That'll actually be really relevant because that's going to be the canonical example that we use today. And you will see a lot of other data structures as well. Trees are pretty common, and hash tables as well. But linked lists are a great simple example. Other observation. Most of the time this state is read. So you will write to things, but most of the time it's actually read. So given that that's the case, how would we actually create an implementation of a data structure that supports concurrent access and mostly has readers and isn't too painful to interact with? Okay, so we have this really simple type. Notice we just have two values in each linked list node. So we have types of struct list node A and B, pointer to the next node as per usual. So this is a singly linked list. And we have another list node star for the head of the list. And so we might have something like this. 4 nodes in the list. The last node's next pointer is 0 or null. We're all familiar with this, right? This is very straightforward so far. So we have various operations we might want to perform. I need to iterate. Okay? Somebody asked a question about that on Piazza, about this aux thing that you can use to pass values in to some of the iteration operations. Straightforward to do. Nobody would struggle with this, I would hope, at this point. You're in CS124. Insert a node into the list, modify a node in the list, remove a node from the list. These are all easy. Maybe you even have like reorder, reverse, those kinds of things you might want to do. We're all familiar with how to do that stuff. Okay? But I want you to think about the fact that most of these operations will require multiple steps to do the operation that you want to perform. Okay, because you have values, you have pointers you need to manipulate to modify the list itself. Okay, so if we had concurrent access, we would expect we would run into issues. Okay, and the main issue is that we have these multi-step operations that can be interleaved, and then the interleaving can cause all kinds of problems to occur. So let's say that we have one thread, T1 here, with a pointer to the first node in the list. It wants to find the node with A equals 12. And we can all eyeball this and say, oh, that's the last node. And then we have another thread that's trying to insert a node into the list at the same time. So it's conceivable that this could happen concurrently without explosions, but it's also highly conceivable that it could explode quite badly. And so it all really comes down to the fact that T2 has to do a whole bunch of operations at once. So we have to allocate, and I'm using malloc even though we're inside of a kernel. Typically that's not how kernels do it. They'll have their own kernel allocator for reasons. I can't remember if the lectures for that have already come or if they'll still be in the future. But there are, I think, 2 lectures that I give in this class about how kernel allocators work. So they have to play well with virtual memory so that you can use each 4 kilobyte page as much as possible. It's a little bit different problem than user space memory management. But anyways, that detail aside, we have an allocation, we get this node, we fill in some values that we care about, we set the next pointer, new next equals p arrow next, because we want to pull that out, and then p arrow next equals new. Now, so this is a series of steps. We can try to specify these in a particular order so that ideally other things accessing the list will not freak out if they see our new node, but the problem is that both the compiler and the CPU may reorder these things. That's one of the things that we talked about last time, is that both the compiler and the CPU are able to reorder things. So we could have the allocation occur, and then we could have it joined into the list and then initialize the values, and that would be really bad for people finding this incomplete node. We could initialize p arrow next first, and then somebody gets to a node and they have an invalid next pointer, and they just walk off into wherever in the universe. So this could fail in a lot of ways, and it would be even worse if you had two writers trying to do this at the same time. Right? That would be even more horrifying, because now both writers would be trying to write over the first node's next or something like that, and then we could get all kinds of terrible things happening. So we have these operations, and we'd like them to be a critical section. We'd like to ensure that only one thread is doing those things at a given time. So that's kind of a critical constraint that we have to make sure that this works correctly. Okay. So how would we do that? Well, like I said, last lecture we talked about a whole bunch of mechanisms that one could throw at this problem. And so a really simple solution would be, let's just put a lock in there. Let's just guard the whole thing with a lock. And if you want to read the list or you want to modify the list, just acquire that lock. So ding, with PowerPoint magic, we go ahead and add a lock in there. And of course, you can think about how you might want to design this so that it'll work from whatever control paths are accessed. So I say here single core system. If you're in a trap handler, or you have state that's accessed from either a trap handler or an interrupt handler, well, so then it's called from either process context or interrupt context. You could disable interrupts. That would probably be necessary if it's accessed from both contexts. If it's only from process context, you could use a lock. No biggie. Multi-core system, you could use spin locks and also disabling interrupts, depending on, again, if it's accessed from process context or interrupt context or so forth. So we know how to do this, or at least hand-wavy, we know how to do this, right? We know how to use a lock to guard this thing. Important question. Why do readers have to acquire the lock? Remember that writers are the ones causing all the problems, right? Because they have these multiple steps they have to carry out. But the thing is that we need to protect the readers from the writers as well. And so we have this issue that even though I'm a reader and I'm not doing anything to the list, just to make sure I see valid state, I have to acquire this lock as well. And so this solution has this really nasty characteristic that we have this one lock, and everybody has to acquire it, whether they're mutating the state or not. So this is kind of a real issue with this. So what's the obvious issue? Readers really shouldn't block readers. They're just reading. They're not manipulating this. So that would be really nice if we could figure out a way to prevent readers from being blocked by other readers. Okay? And like I said, remember the initial statement, which is that this is mostly going to be read. So we have kind of this overhead that we're imposing for everybody just because writers can make things a mess. Okay? We don't mind if writers hold exclusive access. That's perfectly fine. It would be even better if we could have writers in different parts of the list not care about each other. That would be really cool. But at the very least, we should be able to prevent readers from having to wait for other readers. That doesn't make any sense for this. Okay, so the way that we describe the issue with the system is we say that it has high lock contention. Lock contention is basically how much time am I spending waiting on locks rather than doing useful work. Okay, that's what lock contention is. You can actually quantify it as just the percentage of time a thread spends waiting. Okay? And you can imagine that as the number of readers goes up, the lock contention would go up. So this is terrible. This is a pretty bad approach. Now, what's an obvious improvement on this? Sticking with the lock approach, but what would be a nice, simple change we could make that would greatly improve the concurrency of the system?
Like two locks? A read and write lock?
Yeah, if we had like a reader-type lock and a writer-type lock, then we could probably make this a lot better. Because at least that way, readers could access the list concurrently, but then writers would still require exclusive access. Okay, so that's one thing that we can do. Throw a read-write, yes, sir.
Does this still have high lock contention on a single core system?
Using a read-write lock?
Without splitting the locks into a read-write.
Would it still have high contention on a single core system? Conceivably it could, and the reason why is because if you have preemption, then a thread could be preempted while it's holding the lock, and it won't release that lock. I mean, remember that we talked about that as well when we talked about deadlock, is that typically when a thread is preempted, it still retains all of its locks. And then so if you switch to another thread that would like the lock, then basically it would immediately yield. So ideally you would see somewhat of a reduced, how shall I say, there would be less cost associated with that system, but you still would have low concurrency and high contention. Yeah, that's a good question. All right, let's see. So we throw a read-write lock at this, and basically the idea is that readers no longer block readers. They can acquire shared access somehow to this data structure. Writers must acquire exclusive access, and shared can overlap with shared, but shared can never overlap with exclusive. And exclusive cannot overlap with exclusive. That's an obvious one as well. Okay, so that's nice. We have these two operations. It depends on how the read-write lock is constructed. Like I was quite interested, some of you may be familiar with this, but Java's read-write lock actually is a double lock kind of thing. Like you can say, I want the read lock, and you get the read lock. I want the write lock, you get the write lock. The POSIX read-write lock is just a single lock, and you just say, I want to read lock it or I want to write lock it. So it depends on how the abstraction is constructed, but we can just imagine we have read lock operations and we have write lock operations as well. So you see all these alums floating around right now. Okay, so that will help. Now we get more concurrency. Now we get more readers able to access the list right away. And so this is nice. We reduce lock contention. But there are still some things that are annoying. Readers still pay a price. Not their own fault. They're just reading. But they're still paying a price because writers can mess things up. Okay? So we actually call this lock overhead. And this is one of the things that's kind of unusual. Even though, let's say that like 99% of the time you're reading, 1% of the time you're writing. So most of the time when you go in to get that read lock, no one is blocking you. You get it right away. You still are spending hundreds of clocks just acquiring a lock. And that's annoying. Why would you waste this time, hundreds of clocks, many, many times, just because you're worried about somebody doing a write infrequently? Okay. So that's annoying. Now, the other thing is that writers still block everybody. And you might say, well, that seems unavoidable. And I suppose, at least with a single lock, it is. Right? Writers still block everybody. It's still a problem. So the question is, can you come up with ways to manipulate this list that doesn't require writers blocking everybody? And it's interesting because this would be a fun problem to discuss. And I don't know if there's any classes anymore that talk about this stuff. I wish there were, if there's not. But how you deal with these kinds of concurrency issues is quite an interesting problem. Okay? I'll show you a simple one. Okay? And I just say it's conceptually simple because it actually turns out that it makes your life significantly more complicated. But one of the questions that you typically ask with these lock-based systems is, what is the granularity of the lock? In other words, how much data is each lock guarding? Okay? Before we had one lock guarding everything. And then we could change it to a read-write lock, and now we can be more clever. But we still saw that writers were blocking everybody else. So the question is, can we actually have more locks that guard smaller pieces? And then maybe we can get a higher concurrency from this kind of a situation. Okay? So what we could do, for example, is put a read-write lock in each node. And that way, you access a lock, or you access a node, you want to do stuff with it, well, you can acquire a read lock on that node, or you could acquire a write lock on that node. Okay? So think about the things we've talked about. Well, lock acquisition is expensive. Hundreds of clocks are burned each time we acquire a lock. We're mostly reading, so now we're multiplying that cost. That's not great. Ideally, though, writers will just be able to lock part of the list. Or maybe they'll lock from that point on to the end if we're talking singly linked lists. So, not great, but better slightly. So, something like this. You have a node lock for each node, and of course you'd still need a lock for the head pointer as well. You'll still want a read-write lock for that as well. Okay. Not horrible, slightly better. Okay. So you'll notice I have a little skip to RCU link at the bottom of this. I'm going to skip about 10 to 15 slides exploring this approach because it introduces a significant number of complications. Like, if I want to access the next node, I have to hold a lock on the current node so that nobody changes it out from under me, which means I have to hold this lock until I step to the next lock, step to the next node, and once I hold that lock, now I can release this one so I move forward. So the way that you access this data structure is more complicated if I add more locks. So there's a lot of exploration of that. You can read about that. That's how some of the best lock-based data structures approach these problems. So, but hopefully you're starting to see why I actually am super excited about lock-free data structures and why I would love to put together some material to talk about it because it just revolutionizes all of this stuff. I mean, I've been programming with locks since the mid-90s, so it's so powerful to move away from that. So it's pretty neat. So anyway, there's a lot of issues that you run into with lock-based systems. You either have simple coarse-grain locking, which sometimes is all you need. If you have a system where all you need is the coarse-grain locking, then do that. That makes it really simple. But it does end up blocking everybody. You get high contention if you have a highly concurrent system or would like one. You can go fine granularity, but then you have huge lock overhead, better concurrency, but huge lock overhead. Okay, let's see. There's a few other issues that can show up. Locks in interrupt context are always sad, so you can't really do that anyway. Okay. So, the question is, what are we actually trying to solve? What is the issue we're trying to prevent? And really, if you think about it, the linked list mangling and all the kinds of problems there, we're trying to make sure that nobody sees invalid state. That's really all we care about. We just want to make sure nobody sees invalid state. So this was the example. We had to do all these steps, and we didn't really have any guarantees about what order to do these steps. And so if you're thinking about that, especially in the context of the last lecture, hopefully you're looking at this and thinking, well, I know we had these barrier things. We had optimization barriers that kept the compiler from reordering things at specific points. We have read-write barriers. We could use that for the CPU so the CPU doesn't reorder things. Maybe we could leverage that to improve this circumstance. Okay? Because like I say here, the big part of the problem is that we just can't guarantee the order of these operations. Okay? And this is the funny thing. You think, okay, what is the fundamental purpose of a lock? Well, it's basically allowing us to not care what order things happen in. Okay, well, what if we can actually exert some influence over the order of things? Okay, so T2 inserts a node. Why don't we break it into two steps? One is doing all the initialization that nobody else should see. Okay, so we allocate the node, we set these things. We really do not care what order these occur in. Because at this point, this should not be visible to anybody else. Okay? So whatever the compiler decides is a smart thing to do, cool, we don't care. Okay? So T1, think about this from T1's perspective. It's walking down the list, it doesn't care because something is happening, but it is not visible to T1 at all. Okay? So that's step one. Then step two is that we make this change to the list in some atomic way. So we have a single step that changes the list into the new version. And so other threads will either see the old version or the new one. But both of them will be correct. Okay? So both of them will be coherent in some way. Okay? So we make that change in one step. And if you think about it, we're just writing to a pointer. And pointers are data bus width size, right, on all reasonable processors. So this should be a single word write. You would expect that most processors can do this in a single atomic operation, even on a multi-core system. Okay? If they have appropriate coherence built into their shared caches and things like that, then it should be fine. Okay? And so the result of this is that the reader never sees an invalid version of the list. Okay? That's already, hopefully, you're looking at this and saying, well, that looks really simple. Where's, Donnie said this is going to be a complicated lecture. Where's all the complication from? Okay. So basically, we just need to build a little infrastructure to help this all work. Okay, so the mechanism is called read, copy, update, because, again, you're expecting that mostly you have reads. When you want to make a modification to a list, you basically have to make a copy of something, and then you have an atomic update. So that's where read, copy, update comes from. And like I say here, it is a kind of mutual exclusion. If I have time, I'll tell you about some of the caveats that are important to be aware of. Okay. So, changes to data structures made in such a way that concurrent readers never see intermediate state. Okay. So changes basically have that two-phase thing that you should have already seen. So you have the setup. I need to create something that needs to be incorporated into the data structure. And then you have the actual modification, which has to be an atomic step. Okay. And RCU, so read, copy, update. The form of the change is always changing a pointer. Okay. That just tends to be the way that they do things, because these are sophisticated data structures, like I said, trees, lists, hash tables. So that atomic change is always going to be a pointer change. Okay, any questions so far? This is easy so far, right? This is like not the hard part. Okay, so the way that typically this is presented is that this changing of a pointer is considered publishing a new change. Okay, and so people like to think of this in terms of publish, subscribe. So again, T2 prepares a node, and then they publish their change. Okay. So basically, we just need to make sure that step 2 only happens after all of step 1 is completed. So optimization barrier, write memory barrier. Okay, that's all we need to do. Barrier right here, and then we can be sure that both the compiler and the processor will have completed all of this work before this step is taken. Okay, so that's not hard, right? That's really easy to do. Everybody with me? Oh, that part's easy. Okay, so we have a macro. This actually, I'm going to show you a full implementation of RCU. It's crazy, but it fits on a single slide. So we want to atomically publish a value to a pointer. So we have this macro, RCU assign pointer. I don't know if you've seen macros of this form before, but it's a nice, simple way of injecting code into your program. So it's a very limited templating mechanism in C. So notice we have the curly braces and the parentheses. That's all just to make sure that if you use this in a condition or something like that, which would be dumb, but one could, that it doesn't screw up parsing for everything else. So we have write memory barrier, particularly if you're on a symmetric multiprocessor machine. This also includes an optimization barrier, and then we just do the assignment, right? How hard is that? Now, what's cool about this is it's just assignment, because these things are going to be word-aligned, and on x86, word-aligned writes are always going to be atomic. So we already did that, right? So that's publishing. So we update our code, and instead of having just, what was it, p arrow next equals new, now we say RCU assign pointer. And that will do the appropriate steps of ensuring that there is both an optimization barrier and a write memory barrier before this step occurs. Yes?
Sorry if I missed that, but is this in Pintos?
I'm sorry?
Is this in Pintos?
Is this in Pintos? I wish it were, but it's not.
Right, it's not.
I'm showing you something in Linux. And dude, it kills me. I mean, this is what I was saying. I said this a lot last lecture. This is why I'm really seriously considering putting together some Lockfree problems and maybe having a CS11 track on it or something, because this is really cool stuff. And to me, this is state-of-the-art. I mean, this is state-of-the-art like 5 to 10 years ago. Pintos is old. And, I want you guys to be able to play with the state-of-the-art. So maybe one day, if anybody wants to do a CS81 playing with Lockfree data structures and help me put together a CS11 track, I will hire you in a second. So, yeah, But anyway, this is basically stuff in Linux. Pintos is it's all lock-based. Lock-based and interrupt enabling and disabling based. Okay, so T1 needs to see the current state. Okay. Now, this is an interesting thing because so T1 is just traversing the list looking for a node. This is code that you might have for that. Notice we just pull the head pointer out. So now let's list node start P. And we look at it, we do stuff, and then we just say P equals P arrow next. So remember this whole concept of publish subscribe. So we have RCU assign pointer, that's publish. And now we have subscribing in here. This is a subscription where we access head. This is a subscription where we access P arrow next. I want to see the current version of it. Okay. Okay. So we need to make sure that. Now this is weird. I mean, you may look at this and say, what kind of insane processor would ever violate this rule? We need to make sure that when we read P equals P arrow next, that this must finish before we try to access P arrow A and P arrow B. Right? No human being wants to program a processor that can possibly misorder these things. Sadly, those processors exist. So what that means is that when you do this step, you need to make sure that you put a read memory barrier here if you happen to be in one of those insane worlds of despair that do exist. Thankfully, x86 is not that way. x86 will do the intelligent thing. It'll make sure that this read finishes because it'll see that there's a data dependency between P and accessing dereferencing through it. Okay. So x86 will be really nice. Dec alpha, wish that on your enemies maybe if you really hate them. But thankfully we don't have to live in that world. Okay, so again we have RCU dereference. So this is the subscribe operation. And notice, we just pass in a pointer. And what this macro does, it's really funny, because what does it really do? Well, it initializes a local variable value. It accesses it once. It does a read memory barrier to make sure that that read operation finishes. And then it just evaluates to that value. Okay. That seems like a lot of steps, but they're necessary on crazy processors. Okay. Access, oh yeah, so let's talk about this first of all. Remember that I said on IA32 or x86, we don't need to put in a read memory barrier because the processor isn't insane. Okay? And since it's not insane, that SMP read barrier depends to no op. It goes away. How cool is that? Access once just makes sure that the compiler doesn't pull that value from a register. Because remember, we want to see the latest published value, which means we have to read it from memory. So access once. Basically, you can imagine all it does is it casts that thing to a volatile so that forces the compiler to read from it, and then it reads from it. That's all it does. And you'll notice even further that it reads from it and then returns it immediately. So what will this actually do? Almost always, if you have a compiler that doesn't suck, then this is going to end up emitting one instruction. Move from, or dereference the pointer and get the value out and, return. That's going to be the one instruction that this really generates. Okay? So, what does this mean? Well, so far, publishing was just writing something and then having a write barrier. Subscribing is just reading it. So this is a really inexpensive operation so far, right? And, it's crazy because you might think, well, the devil is in the details, and there are some details we have to iron out. But this is super efficient compared to the overhead of locks. Okay, so here's the updated version of T1, thread 1, because it's traversing the list. Notice we have RCU dereference wherever we access stuff. So this is great. Writers, so far the real cost is that writers have to copy things. But we already asserted that writers write infrequently, so it should not really be a serious situation. They have to use a write barrier. That's okay. We want sanity, right? We don't mind. Okay. Questions so far? All right, so that is publishing and subscribing. But that's not the whole picture. We have a few other things that we have to figure out. Here's another example. We want to take that second node with A equals 19 and B equals 2, and we want to change it. We want to change B to be 15. Okay? Now, the challenge here is, remember, this is read, copy, update. So if we want to change that node, we can't just change B to 15, even though probably it would be atomic. We have to actually make a copy and make our changes to the copy and then publish those changes. Okay? So we do the steps like we did before. Copy equals malloc, copy A across, set B to 15, and then set up the next pointer. Okay? That's all the setup. And then we do RCU assign pointer to make the copy available. So threads will either see the old version or they'll see the new version, but they won't see some mangled, twisted intermediate step. Okay? So this is just like we talked about before. Okay, so readers fall into one of two categories because this is an atomic operation. They either see the old version or the new version. Okay. Everybody with me? So this is cool. Like this is so far it's fine. So this is nice. This is a good result. Everybody sees a valid version. Okay. What else do we have to do? Yeah.
If like some other thread has previous stored in cache, then you would want to like invalidate that cache to update to.
We might want to. So you're saying that some thread sees this old version.
So there's looking at holding a pointer to previous.
Previous. Oh, okay.
And that is stored in the cache, and then
yeah.
when
So
it says previous.next, it still points to P.
Yeah. So let's assume that our processors take care of that. We don't have to think about it. Yeah.
We have to frame the memory associated.
Yeah. You guys see that? Like somehow, we just made a new version of this node, which means this guy is like obsolete. We need to delete him at some point. So when do we do that? That's the question. If we just threw in here a free, what problem might we cause? Remember, threads fall into two categories. Readers fall into one of two categories. They either see the old version of the node or they see the new version of the node. So, yes?
So those who see the old version will simply see that something disappeared.
I'm sorry, should you repeat that?
So those who see the old version of the node will just see that something disappeared.
Yeah, or worse, they won't see that it disappeared. They'll see that maybe parts of it got stomped on, or suddenly somebody allocated it to something else, so they'll see weird garbage, or you can imagine this could explode in like a bunch of different ways. But the big issue is we don't want the writer deleting the old node out from under any readers. This is where all the complications come in read, copy, update. Okay, so we talked about that. Okay, so this is the part that is tricky. We have to figure out when we can reclaim these old things. Okay? And so like I say here on the slide, we have to make sure that data is only deleted after all the readers are done with it. So how do we tell that the readers have actually finished? This is where all the subtlety is. Okay? So what we do is we demarcate that there is such a thing as a Readsite critical section. And basically what that is you're looking at pointers. If you think about it, the whole issue is making sure readers are done looking at things. So we'll just put some demarcations saying the reader is looking at things. So you enter a Readsite critical section, more or less, when you start RCU dereferencing, and you leave the Readsite critical section when you no longer are using those pointers. Okay, so you RCU dereference into P or something. I'm not using P anymore. Then I left the Readsite critical section. So we actually provide operations that denote the beginning and end of these Readsite critical sections. Notice RCU read lock, RCU read unlock. Okay? That's basically all we have to do for the Readsite critical section. So readers now say, hey, I'm starting to read junk, and I'm done reading junk. So here's the reader thread updated to declare its Readsite critical section. Not complicated, right? We haven't really done anything insane. We're just putting in little demarcations saying Readsite critical sections. So here's the rule about Readsite critical sections. They are critical in one way. They must be completed without blocking or yielding, or I guess you would say terminating, but if it terminates, then technically you are leaving the Readsite critical section. But basically, you're not allowed to get off the CPU until you're done with that Readsite critical section. Okay, so you enter the Readsite critical section, you get the CPU till you're done. You can't be preempted. Timer can't kick you off. So this is something that the OS has to implement. This is something that the OS kernel has to be aware of. Okay. So just eyeballing this, barring preemptive multitasking, do we do any long IOs? Definitely not. Do we yield? We definitely do not. Okay. So we're okay. This code is fine. It's just looking through the list. And as long as okay, so I should be careful about preemption anyway, because technically this is the kind of technique you use inside the kernel. So it's not going to be preempted anyway. We're inside the kernel. So basically, this notion of Readsite critical sections can be used to figure out when stuff can be reclaimed. Okay? So notice I have time, program is running, I have readers overlapping, it's a beautiful world, and they all start with RCU read lock, they end with RCU read unlock, and then some number of times inside they call RCU dereference. Okay? Maybe right away, maybe a little bit in, who knows. Okay. Now somebody publishes something, so they call RCU assigned pointer. Okay? RCU assigned pointer can never occur exactly where an arrow starts or exactly when an arrow ends because it's atomic. Okay? So that allows us to divide readers into two groups. And the way that I describe this is nice. Readers that might see the old version, like reader 4 might see the old version, but maybe they saw the new version. We don't know. All we know is that they called RCU read lock before RCU assigned pointer was called. Okay. So what readers might see the old version of the data? Probably pretty obvious, right? Remember, the arrow starts where RCU read lock is called. It ends where RCU read unlock is called. When I call RCU read unlock, I'm saying I don't care about this thing anymore. I'm not looking at it. Okay? So I only care about stuff inside this span of time. Okay? So readers that might see the old version of the data, well, if you have an arrow that starts on the left side of RCU assigned pointer, then I might see the old version. Who definitely cannot see the old version?
5, 6, 7.
Yeah, 5, 6, 7. Anybody whose arrow or their RCU read lock call is on the right side of RCU assigned pointer. Okay, so this is kind of interesting. So when can we reclaim the old version of the data? Should be obvious, right? Well, we got to figure out when these arrows that started on the left of RCU assigned pointer, when those arrows end. And we know that there's an RCU read unlock called over here. So we just figure out, okay, what's definitely not 5, 6, or 7, like was said. So right here, right? This is where, that's the first possible point that we would be okay deleting. Okay? So it'd have to be somewhere here. Got it? Now, I say when can the writer reclaim the old version of the data? Does it matter if we wait like 15 minutes after that point? We just hold old data. Nobody's going to see it, but it's there. So it'll kind of waste resources. But the whole point is that that's the first possible moment we can actually reclaim it. So what this means is that this space in between is called the grace period. And what we're basically doing is waiting for everybody to get out of the part of the data structure that we want to delete. Okay? Questions? Yes?
When you do read lock, do you have to say like which node you're on?
So that's an interesting question. If you are trying to be clever about your RCU implementation, then you would probably want to say something about what CPU you are on or something like that.
Or like which node you are on.
Oh, node in the linked list. Perhaps, but this simple version doesn't actually care about that. Yeah, this is the simplest possible implementation. Like I said, it fits on a slide. Okay, so the writer has to know that there's an end of the grace period. Where are we at? Oh, 5 minutes. Maybe we can do it. So there is another operation called synchronize RCU. Synchronize RCU basically says the writer is blocking until the grace period is over. So synchronize RCU is a call. It may block, probably will, and or block. It'll give up the CPU briefly until the grace period is ended, and then the writer will get back, and it'll know that afterward it can go ahead and free. Okay? So this is basically all we've had to do for the writer. Got it? So this waits the grace period, and then we free. So here is the implementation. So how does this work? Well, so remember that we had Readsite critical sections had a constraint that they were not allowed to block. We're not allowed to switch away from one of these readers while we're inside the Readsite critical section. This is actually really important. So here's the question. What's the maximum number of readers that could be in this data structure inside the Readsite critical section at any given time? There's a limit. Yeah.
Number of cores.
Yeah, number of cores on our system. So let me see the right way to, yeah, so same as the number of CPUs. For readers inside the Readsite critical section, it's also on a CPU, and it will be on that CPU until it's done. So, yeah, so that's an obvious one. We want to prevent the OS from preempting a kernel thread that's actually inside a Readsite critical section. Okay. There's a really simple way of doing that I'm not going to spend any time on just for the sake of completing the critical parts of this. But here's the thing. If a particular CPU in the system executes a context switch, well, then it must not be in a critical section. It must not be in a Readsite critical section. Because you're not allowed to switch away from that thread, that kernel thread, until it's out of its Readsite critical section. So here's the simple way that you can implement this. Synchronize RCU could just wait until there's one context switch on every core. Once that's happened, then it knows the grace period is over. Because anybody that was in a Readsite critical section, afterward you switch away, then I know that that reader is finished. Okay. So this is pretty wild. Again, this is like the simplistic version. Here's an implementation of Synchronize RCU. Go through every CPU. Context switch to that CPU. When you context switch to it, you know you context switched away from something else. The thing that you switched away from can't be in a critical section anymore, Readsite critical section anymore, because you switched away from it. So once you've hopped onto every CPU, you know you can delete. Okay. So this is really simple. And yeah, single core? It's no op. That should make sense, because if you're the writer and you're occupying the CPU, and readers can't be interrupted while they're inside of a Readsite critical section, then your presence on the CPU means that nobody else is in a Readsite critical section. You win. Okay. So there we go. That's the argument there. I'm going to rush. Read lock and read unlock. Well, on a multi-core system, they have to disable and re-enable preemption. Because remember, you can't switch away from the Readsite critical section. So kernel supports preemption, you turn that off. Okay. So I'm going to, again, rush to finish this all. Let's see. Yeah, so we'll skip this. Yeah, and again, read lock and read unlock on a single processor system also end up being nothing. Okay. So how cool is that? So RCU, really awesome. And I'll have to tell you this one thing. Again, I think we're basically up against it. So let me try to just tell you the most critical things. Really simple idea. we're just maintaining multiple versions of data structures and publishing them in controlled ways. The subtle part is all in figuring out when to reclaim things. And what you're doing is like locks are simple, really. Plop a lock down, I acquire it, I release it, no biggie. RCU basically requires changing the developer's approach to managing concurrently accessible data structures so that they're maintained in a particular way. So we have all these rules that you have to follow when you're using them, but when you follow those rules, you get great results. Okay, so no locks, extremely lightweight. That's the entire RCU implementation. And again, this is a naive, basic approach demonstrating that it's possible. And it's really only complicated when you're on a multi-core system. If you're on a single-core system, most of this vanishes. Okay? So, yeah, you have to have a lot more readers than writers. If you have more than one writer, it even becomes more complicated than this because you have to do a compare and swap. And that's one of the things I haven't talked about in here, or compare and set, I really should say. Because you have to make sure some other writer didn't beat you to the punch. That's an important detail. And in RCU, those kind of situations with multiple writers can become really damaging because you have to kind of start all the way over. Okay? Consistency should not be a strong requirement. So if you have this loosey-goosey stuff with multiple versions, you have to be in a situation where that's okay. Like this does not work well for databases and transaction isolation, but works great for OSs. Okay? So yeah, it may be better to rely on locks if you have either one of these requirements, or violate one of these. Okay, last thing, yeah, so like I said here, many parts of Linux satisfy these requirements. So look at this. RCU is really becoming ubiquitous within the Linux kernel. Okay, I like that plot a lot. That's why I would love for you guys to have some experience with it, but maybe we'll arrange for that in a different course. Here's the other thing that I love. So this is the overhead of acquiring a lock. Notice nanoseconds per operation. As you increase the number of CPUs, you know, you can get a 32 CPU machine and so forth nowadays. So as you scale the number of CPUs, lock and unlock operations become really expensive. But look at the cost of RCU. You can't scale much better than that, right? So RCU is a beautiful thing. The last thing that I want to mention is, yeah, so you can read about this. There's some important improvements made on RCU so that it's actually usable in the real world. I have a lot of references in this lecture if you're curious about learning about all this stuff. This guy, Paul McKenney, this is his PhD work. So you should definitely read his publications if you're interested in that stuff. And then the other thing that I wanted to show you is lock-free data structures, because this shows how to handle the situation with multiple writers in more detail. So it's pretty crucial to understand that part of the picture as well. All right, any questions? Hope you enjoyed it. We'll see you next time.